Yeah, welcome to Practical Data Science and how to track your development process with DVC. My name is Mark. I'm a data architect, data engineer, whatever at CodeCentric. So taking care about everything that's around data, big data, and data science. And
I'm Tim. I'm also at CodeCentric, working as a data scientist. And as I'm being a lazy person, I'm always looking for some nice tooling which helps me getting around better doing data science. And this is also pretty much the topic of this talk.
cool. So
Yeah, also.
awesome. Let's have a short look what we will talk about. So instead of showing you how the framework works and just going the happy path, we want to show you a real end-to-end use case. And this is our short story. We will build a classification system that can detect different fruits. And just imagine how awesome this would be for supermarkets and retailers for automatic billing. And short for the agenda, so I will start a little bit with talking about what is data science, how can you model, how can you build a model interactively, but also what are the implications of data science in your software development process. And right after that, Tim will show you all the nitty-gritty details, how you can solve these problems. And in the end, you see a nice live coding session and a nice live session how we build a continuous deployment pipeline for machine learning models using Tensorflow and Tensorflow serving. All right, let's start. So let's build a machine learning model interactively. A short question, so how many of you have experience in machine learning? Or, all right. And all the rest, no experience at all. So you will now see how easy it is to be a data scientist. Cool. So we will use Keras. Keras is a nice, easy-to-use front end to build neural networks and deep learning algorithms. I have to put this away. So, can you still understand me? Awesome. Okay. So what you see here is basically, it's called a Jupyter Notebook. It helps you with live coding in Python right in the browser. And the first thing what you do when you start building something interactively, you explore the data. So you see what kind of data do you have. We have a data set from Kaggle with a lot of fruits inside. And what you see here is we have to load this data, have to define it a little bit. This is not needed, but we have to somehow need a generator that gives us data sets that we want to train to our model. Because we have machine learning, that means we try to learn something from the information inside the data. Just look at this one here. So we do something with the information we get, and we normalize the images because for algorithms it's much easier to learn information that is between 0 and 1 instead of 0 to 255 that we have normally in images. Keep this a little bit in mind because this might be interesting when we go on later and when Tim starts to explain some things. Okay, so cool. Oh shit!
Awesome, huh?
Awesome. What did you do?
I don't know.
Okay, doesn't matter. Oh, this presentation sucks. Just give me a second. Ist das gelöscht?
Mm-mm.
Ja, den Data Order nicht mehr.
Oh, yeah, then that doesn't work.
Hast du den gelöscht? All right, we go on without nice pictures, but it doesn't matter because I will explain you the code. In order to start with our model interactively, what do we have to do? We have to first take care, how do our classes look? How do our images look? What are we doing? In order to this, you need a little bit of code that you can write here. And normally, if everything is in place, which was in fact 10 minutes before, you would see here how many kind of awesome, it still works. See, this is the magic of data science. So what you see here is we look into our data set, and what we can see is, all right, we have images of bananas, we have images of lemons. Overall, we have 884 different images that we want to work on, that we want to use for training our classifier. And the most important thing, if you do something interactively, is okay, let's first of all see how many images in what class are, because then otherwise you can get really problems if it is really unbalanced. But here it's really fine. Data scientist is happy. We have around 400 images per class. Awesome. And we go on. So we want to look at the images. And we can't because things are apparently not working. But if you would see, if this would be working, you see it's right working in the browser, you would see really nice images of bananas and lemons. And it would show that our data set is super clean. And it has to be super clean because actually it's copied from a Kaggle challenge. So cool, but it's a good, good basis to start initial modeling. And now the nice part for you comes. I assume most of you are software engineers somehow. So at least that's what I assume if you have no experience with machine learning before. Here we show you how easy it is to build a classifier, in fact, with Keras as a front end and TensorFlow in the back end. You see, we import the Keras library, and now we start with modeling our neural network. A neural network is nothing more than a lot of small functions. Basically, they are the representation of your neurons in your brain. And all these small different functions, they are connected using weights and edges, or weighted edges. And you put these into layers and subsequently move information from the first layer to the last layer. So in the end, what you want to have is a percentage, is something that tells you, hey, this is a banana for 5%. With a 5% probability a banana and 95% probability it's a strawberry. And here, this one here, it's a convolution. Somebody heard maybe of it. It's basically an automatic feature extractor. And the nice thing is Keras has everything built in for you. So what you can do is, I want a convolution. Oh, I want a normalization layer because maybe some data is going out of bounds when propagating it through it. Maybe we want to summarize some features, which is the max pooling. It's all done for us. Here we put in some noise into our model because we have so clean data. We have to artificially make our data a little bit dirty. We flatten the whole thing. That is, everything that we are extracting, we put it in line. And then we basically use a classical neural network, which is basically 20 years old and even older. And in the end, we say, okay, build a neural network with the output of two classes right now, banana or lime, or banana or strawberry. And what we want to have back is basically a simple number between 0 and 1 per class. So that's in fact a machine learning model. So data scientist work seems quite easy. This works, which is cool. And we want to start to train our model. The same thing here. We all do it in the browser, and this is like real data scientist work. This is the environment that you see here. It's just a nice look at it. But in fact, you can everything do in your browser. You can do everything in your browser. We started, of course it won't work because everything else didn't work. But you would see here a nice history of 5 epochs, like 5 training sessions where we train these 800 images over and over again until we can really good distinguish between each picture. You will see when Tim is doing it, his code is more stable because he does the engineering part. It will
hopefully.
And this is our code for evaluation. Awesome. If this would run, you would see we have an evaluation score of around 99%, which is in fact really nice. If you ever worked with image processing and tried statistical approaches with OpenCV, for example, it would be really easy to distinguish 2 different images and build algorithms for it. But as soon as you have some small changes in it, like the banana is now from has a photo from a different angle, or there's a different lighting, you will start having problems again, and you have to build every case per image. So all these convolutional neural networks and deep learning approaches, they were really a groundbreaking technique to classify images. This is why this everything gets so popular, like AlexNet, ResNet, everything from Google. We built something.
I'm sorry, I see you're not comfortable with this kind of mic recording, so I just need to.
All right.
Just set it as you. It's fine.
Yeah. Can you hear me? No? No. Oh, wow. Okay. I'm a bit silent now. We build everything, and it's supposed to work, right? So, nice. From a data science perspective, we are done. Feature is done. This is what we were basically promising our boss. Now hand it over to operations, to most of you guys, somehow DevOps, development, and it's your problem now. And yeah, well, there are some arising problems with that. Did we take care about integration testing? Not at all. Did we validate the quality? Yeah, for us. And you see there is a data set somewhere which is not apparent here at all. So it's basically impossible to reproduce it somewhere else. And how can I build a continuous deployment pipeline if I can't reproduce what I did before, if I have no tests at all? And what you see here, this is basically, some points are from my side, my opinion. You need monitoring, scheduling, alerting, alarming, and so on, because I come from a not data science, but from a software engineering experience. And a lot of things are basically from Google software engineers that come from the same career path. And they want reproducible trainings. So if you train your classifier, I want to train it on a version data set. I want to train it with version parameters, with a version architecture, and so on. And I want always to have the same result, because then we can start with continuous integration, continuous deployment, and so on. And now arising problems arise. The data set, which is apparently not here today, it would be large. Our model would grow and would be large too. So what happens? We start having problems using Git for everything. From a development perspective, awesome, but how would you version binaries? I mean, putting binaries into the VCS is always bad. From a data science perspective, it's even worse. Now we are working in a so-called notebook, right? What you have seen here. It's all fine, but these notebooks, they are more like binaries. When someone changes something in it and you push it to Git, everybody gets merge conflicts. So we will find a tool that helps us to version really large data sets, that versions large files, takes care of pushing them somewhere, but also takes care of parameters, architecture, and so on. So this is what Tim will talk later about. And what we will also look and find a way for is, how does data engineering, data science interfere with the software development? Because nevertheless, this is my personal opinion, everybody of you will get somehow in touch with data science, get somehow in touch with data engineering. Machine learning, modeling, analytics, it's getting so important, and the term data-centric applications, it will basically overwhelm everything in the next years. And you see here, it's already in. Like, you need the pre-processing. You remembered the small code that I showed you, 1 divided by 55? That's a central point. If you forget this in your application as a pre-processing step, the whole classifier don't work anymore. So there's a lot of things we have to take care about. So we have pre-processing, we have model. Pre-processing and model are bound together. So there's a tight coupling. And we have 2 different processes. Like, we have our application development, which is agile, iteratively. these experiments, they are also iteratively, but they're basically besides that. It's like two teams or a same team, but different people working on it, different features, and this has to be integrated. This has to be integrated in the repository. This has to be integrated in your team workflow. And DVC as one tool really helps us with this. And basically to start and get a little bit more practical, this is my last slide with just theoretics. So what we want to propose today is basically a stack. It's not proposed by us or it's not invented by us, but it's a stack that from our experience works really well. So first of all, Python sneaks into enterprise development. I mean, Docker helps us to abstract different technologies. What before was the Java enterprise software stack, because every operations unit was able to operate it, to deploy applications with it. That's this Docker now in the modern world. And that helps us to use Python, and Python especially because it's the right technology to solve our problems for data-centric applications. So that's a huge ecosystem. TensorFlow and Keras, you have seen how easy it is and how easy it would be to train something that detects their different fruits. And we would have shown it here completely. It takes a minute to build a really strong classifier. That would take weeks if you do it with OpenCV and statistical algorithms. Then we have DVC, data version control, which help us to put this all in a proper development workflow, take care of the artifacts like you would do it in clean software engineering, take care of our workflows and everything. And then we have something for inference, so how to serve this service. And this is TensorFlow serving. And the cool thing that we show you is this is super sleek and easy to use, because we will build a continuous deployment pipeline for machine learning models right here. And you will see in reality how we can change something and directly deploy and version a new model. That's the idea of today. And I would hand over to Tim now. He is showing you the real good stuff.
All right, thanks. I hope that my code snippets are working a little bit better. I might have deleted the wrong data setting before. So Mark just presented you a possible software stack, development stack for the development with data science, and I'd like to go into that a little bit more in detail. So the first technique we're looking into is DVC, which is data version control. And so you might ask yourself, why should I actually use that? Why is that any useful? And the answer is pretty simple, because it gives you reproducible results. Data science is a very experiment-driven field. A couple of scientists which are here in the room will know the situation where they are sitting in front of their Jupyter notebook or their PyCharm and they are testing things out, maybe a new hyperparameter tuning. Maybe they're dropping their feature reduction to see if it makes any effect at all. And so we're scribbling around. And we are retraining our models over and over again, and we maybe have an evaluation journal where we write down our accuracies, F1 scores, whatever. But we rarely think about storing our models to use them later on for later evaluation. And the same holds for the data, right? We have our data lakes somewhere, and we're aggregating it into our train set or test sets. So we're adding features to see if they work, we're changing them, we're removing them again because the feature reduction show, okay, that's not helpful at all. And so we again have like a huge pile of different data versions, and we have so lost track of at which model we've used which data. So this is a very common situation, right? And the other aspect is that data science is also collaborative. You're very rarely working on your own. Just in software development in general, you have a team with other scientists and engineers you're working with. And so everyone is doing his own thing, but you also want to share results. You want to show like this cool new feature reduction you've implemented. But if your model takes 5 hours to train, and you can only give your colleague the Python code, then he has to train it for 5 hours as well. This is really inconvenient, isn't it? So this is where DVC comes into the game, because it provides you this ability to do reproducible results. And the largest aspect of that is obviously the versioning of the data and models, or in general large files. So DVC uses a technique which is basically the same as Git LFS, if you've heard of that. So you have your normal GitHub, GitLab server, and you're interacting it just as always with your code, regardless whether it's Python, R, Java, whatever. And for your large binaries, like the model or the data, you have a second remote storage, like on cloud storage or AWS. And so for these files, you generate automatically a metadata file, which stores the path of the file and the hash sum, and maybe some additional information. And so the hash sum will detect automatically whether a file has changed and whether the metadata file has to be updated as well. And you put your metadata file into your GitHub repo with your code along. So that's really neat. And the other aspect that DVC provides you is the ability to optimize your reproducibility. If you have a very long workflow with, I don't know, data aggregation, data preprocessing, training, evaluation, deployment, and whatever else, it just takes a lot of time. But if you're able to actually reduce it in different steps, and you only have to reproduce those steps that have changed, then you're gaining a lot of value and time. So with DVC, you're able to define a pipeline by saying you have a couple of stages. And each stage is characterized by dependencies, so which affect the result, defined by kind of processing, usually your script, the model code, whatever, and output artifacts, like the trained model. And so then you can combine those stages together by saying, well, my artifact, my output of the first stage is the dependency of the second stage, right? So if the artifact of the second stage changes, DVC will see, okay, my dependency has changed for the second stage, so I need to rerun the second stage as well. And so this goes on and on and on. But if like the data hasn't changed, but only some configuration for evaluation, you don't have to rerun the whole pipeline, and you're saving potentially a lot of time. So this is so much as an introduction for DVC. The other technique I just want to very briefly introduce is Tensorflow serving, which is a very lightweight serving technique for machine learning models. As the name suggests, it supports TensorFlow graphs, but you can also extend it for other types of models. So what it basically does for you is it provides a platform, a server, where you, as a developer or a scientist, can upload your models. So you've increased your accuracy, and so you say, okay, this is neat, I want to put that into production. And so you're uploading it to the model server. And on the other side, you have your client, so maybe your self-checkout in your supermarket, and he wants to detect which kind of fruits it got presented. So it just asks for a prediction. It does a request to the server, and so the self-checkout doesn't have to know anything, almost, but just where to put the request into. So this is the other technique that we're using as well for a little tryout experiment, whether we can actually do fruit classification with the tool that we've just introduced. All right, so this is again just the overview. You already know basically everything. The tricky part is we are going to try it live on our webcam. So since we don't have the ability to put a self-checkout machine here. So let's see if that works out. 50-50 chance, I'd say. All right, so in the first step, we need to prepare our DVC, our data version control, right? And the nice thing is that it goes really well along Git, so it also shares a lot of functionality with Git and the API, basically. So we start by just initializing our Git and our DVC, and DVC asks you to do anonymous usage analytics. Who cares? That's fine. And just as you do in a normal project, you're setting up your remote storage location. So for Git, that would be usually some GitLab repo, and for DVC, it would be a cloud storage. For now, I'm just using the temp folder because that's the easiest way, right? So that worked out, great. And now we want to create our pipeline, the one that I kind of already mentioned. We will have 3 steps: load data or prepare data, train our model, and automatically deploy to our TensorFlow server. So for the dependencies, for the load stage, we need our data, which is currently zipped, and a configuration text file. And this one will, this stage will give us a data folder, which will be used for the training. And the train stage will then output our trained model, hopefully, and will give us also a version file. And the deploy stage uses these both information to automatically upload. So let's see if that works. We'll start very simple with 2 fruits. We want to classify bananas and strawberries. And so we define those into our configuration text file called fruits.txt. And then this is maybe the most interesting part, is we're defining our stage here with DVC by saying, okay, DVC run, this is the command for defining a stage. And we want to define a stage called load DVC, load data with the file extension .dvc. And each dependency is marked by a -d argument. So we depend on the script we were going to run. We depend on the zip file, which is just downloaded from GitHub. And we depend on this configuration fruits.txt, which we defined above here. And as the output -o, we will have a folder called data. And the process itself is then the shell script load data.sh. So this will basically mean that each time one of the dependencies change, we will rerun our load data.dvc. And let's have a look at if this works. And it tells us load running command, awesome. And it computes our metadata file for our large files, so the data where we have test set strawberries, test set bananas, and training and all of that. So far that worked out, great. And since we're doing version control here, we need to push everything. Perfect, that worked out as well. It uploads lots of images to our temporary storage. Okay, cool, so that was our first stage. And obviously we have to define the next 2 stages, so let's go very quickly over them. The second one is being the train stage with the dependencies, my Python script called fruit detector and the data directory, and it will give us a trained model, model.h5, and a version file, and it will run the fruit detector.py. And now it will train a model. It's actually the same code as Mark showed us, only that it's working. And we have 5 epochs. It will be highly overfitted. Let's have a look. So this is the loss. It has finished its training with an accuracy of 1. So this is all neat. And it's uploaded to Git and DVC. And the last stage we're doing is this deploy stage called deploy.dvc, which depends on the script, the model, and the version file. And we will run the Python deploy.py. And obviously, again, version control. And this means that while this is running, it will actually upload the model, the trained model, to our TensorFlow model server, which I should have said it maybe is already somewhere, namely here. It's not too interesting, it's just a Docker container. Not much to see here, just for information that this is actually running and uploading it. Great. So, our pipeline is ready, right? We can even have a look at what it looks like. So let's do that to see whether we are all correct. Yeah, that sounds reasonable. That's what I've defined. But I told you we want to do live prediction. Is that actually working out as well? So we will try. I think it was somewhere here. So I have a very simple script, which is just grabbing my webcam right now, if it works. So that's me. I'm a strawberry. That's not surprising. And since we don't have the ability to bring fruits here, we instead have printed out small carts with fruits on them.
Well, let's have a look at our shopping cart. And first of all, let's hope that a strawberry is really a strawberry.
The problem here is the lighting a little bit, since
But it's a strawberry, at least with 99%. Cool. Let's look if a banana is a banana.
Is a banana a banana? Yeah. No, not really. Oh, there
Oh,
it
there.
was.
You see, there it was. I mean, we used a really clean data set.
So the webcam is not really capturing the true data.
But there was our banana. So it's a really bad model, by the way. But the goal is not here to show you that we have a perfect classifier for bananas and strawberries. In fact, what we want to show you is that we can update our model in a continuous deployment style. And for that, I would like to hand over again to Tim, because he will show you how you can solve this with DVC. And I will show you that we also know walnuts after that.
Right, I'll just stop that for a second. So our goal is, like, in a supermarket, you don't only have bananas and strawberries. And since we now have almost shown that we are able to detect that, we maybe also want to buy other fruits or nuts. So we also want now to detect walnuts. And this is where DVC comes in really handy. So what you're able to do, I talked a lot about reproducibility. With DVC, you can just say, reproduce my pipeline, and then you define a stage up to which you want to reproduce. And if we're trying to run that now, it will see whether any stages have to be rerun. And now that I just created my pipeline and didn't change anything else, it tells you, well, I don't really have anything to do. What are you telling me? So it's just doing nothing, which is good. We're supposed to have that. But now I'm changing my very first configuration file, and I'm telling it, okay, bananas and strawberries are fine, but I also really need walnuts. So I'm changing the very first dependency, and so we're expecting the pipeline to completely run through. And that's exactly what it's doing. It's telling us dependency changed. We need to rerun load data DVC. And so it's doing it again. It's reversioning our files. Then it's telling us our train stage has changed. We need to retrain our model, and it's doing that. And so it's retraining the TensorFlow model right now. And at the end, it will also automatically deploy again onto our model server. So it also tells us deploy.tvc has changed. And so if it actually tells it to you right here somewhere. Just successfully loaded servable version. Oh, this is 1, and this is 2. Right. Failed. Awesome. Interesting. I never had that. This is live coding. So the idea is that we would rerun our webcam and would be able to actually
Let's check it if it maybe deployed it anyways.
Oh, let's try it out here. Is that working in any way? Of course not. Great. Maybe it's a banana somewhere. Not really. Okay, anyway.
There's nothing working. Yeah, well, but I think we showed you at least the log outputs from TensorFlow serving. What is the idea behind? Of course, there need to be tests. Of course, there need proper logging and maybe a nice baseline where you can check against as part of an integration test. But what you've seen here is what fails in most data-centric applications for today. A real CI/CD pipeline that's capable of deploying a model somewhere based on an automatism. I mean, a lot of data-centric applications, they start to get developed, and everybody talks about the MVP, the minimum viable product, but a lot of managers are forgetting that the MVP is about features, but not about ignoring every good software development practice. And one of these practices is continuous deployments, continuous integration, testing, and all the automation that happens there. Because what happens is that the code from data scientists, it gets basically shown over on a server, best is via SCP, and as soon as there's some problem, someone has to go there, restart the application or do a rerun, has to do some fixes right on the production servers. And this is a big gap because now machine learning, analytics, and all optimizations that you can do with big data sets, it gets so easy and handy to use. But right now, everything that helps for automation is still missing in the software development process. So data-centric applications and bringing these to production right now is a real big problem. And Google with this whole ecosystem, the Python ecosystem, TensorFlow serving, it really helps you. And tools like DVC is one tool between many. It bridges the gap and helps to finally integrate data science into real software development. And you will see a lot of new applications and business cases will spread out of it. And on that behalf, we are on a paradigm shift. We have a changing role model. Before, data scientists were working in companies, they were doing one-off analysis and were showing that the proof of concept would be working. But now it is working. And you want to have it as a feature in your application. You want that your customer has a benefit from it. So you start integrating it into your application. And as soon as you do this, you have real resources and you have real development artifacts that have to be versioned. I mean, everybody is here because he wants to learn about good software development, and now data science is part of it. So you move from data science to the data engineering, which was basically trying to run this stuff, but now you need something like a data all-star. You need someone who can build a model, who can evaluate the model, but also knows how to deploy that stuff and really knows how to code and what it means to code. And also feel the pain if you bring something into production, because it's always a pain. Indeed, so as said, the trend goes away from one-off analysis. And you see this especially, for example, TensorFlow for Swift, or as it's called Swift for TensorFlow. TensorFlow gets integrated into the Swift programming language like a native citizen. It's part of the language. And this is what I want to say. Everything, so building models will be a first-class citizen. Like an algorithm, like a module a few years ago, machine learning models will really be part of your application in the future. And my personal opinion is we won't be able to avoid this. We just have to know how to use the tools and how to really integrate it into our workflow. Because it's a different kind of development, because you have to experiment a little bit. It's not a deterministic algorithm.
Yeah, I actually don't have much to add here. So we're now thrown, as you just said, with different frameworks. We're thrown at with PyTorch, with TensorFlow, TensorFlow 2. And we're having lots of frameworks and tools we're able to work with. But what's a little bit missing maybe is some help for the production ready work here. So to not only try things out, but to actually get productive here and to get efficient. And what we try to show you in our talk is what a possible software stack could look like if it would be working. But in general, like we need to a little bit to help ourselves to ease our own work. And this is something that DVC can help you, and this is what TensorFlow serving may be able to help you, so you don't have to SCP always your .h5 models in some cloud storage. And so this is maybe an inspiration or an idea for you of how you can get started and how you can get more efficient while doing data engineering and data science. And that's actually it from our side. Thanks so much, and we're very happy to answer any questions.
Thanks. I hope it works. No.
Since this is the future, and I saw that simple models are a couple of 100 megabytes,
Mm-hmm.
and if you want to deploy them locally to a device, for example, on mobile devices, is there some way to reduce the model size and still keep the accuracy? Because I don't think it's reasonable for a simple app to detect something to be a gigabyte that nobody's going to download that.
Yeah, in fact, there are several ways.
No, go
All
on.
right. So if you looked at the recent Twitter feed from Francois Chollet, he's the inventor of Keras. There are like technique right now for graph pruning. So there are now smart algorithms that look into your model graph, into your computation graph, and it can prune some information out of it to make the model smaller. That's one thing. The other thing, of course, is you have to think about smart architectures. So if you compare, for example, AlexNet, ResNet, and so on, it's 200 and what I don't know megabytes big. But is it really suitable for your problem? If we look, for example, for image detection or object detection in images, there are way better models that are way smaller. So you can always think a little bit about the architecture, but right, it's not always feasible. And the other thing, it's already happening. So when you deploy a model, the model that we are deploying, it's not as big as what you have seen when I was building it interactively. So TensorFlow is already smart enough. It takes different parts of the graph, so of the meta graph. So you have several subgraphs in your computation, and one subgraph is for serving. So what you spit out, for example, is the loss function. You don't need it because you don't train it. The dropout layers and normalization layers, they get all thrown out. So at one hand, this is evolving, but you're right. There's no general concept of I want to reduce my size. You have to do smart pruning. You need to use the tools that Google is giving you. Then you can reduce already a lot of the size. And if it's still too big, habits on is a real use case. We are detecting text in your passport ID. You have to use a model maybe that's different, that is a little bit different from what is proposed. Maybe you can get along with a little bit less precision, but you can reduce your model in a huge amount, meaning like taking out 10 convolutional layers because you don't need this kind of precision in your specific use case. And that's also one part. We're doing the really fast development, and this was a really easy model, but it was totally general. I mean, it was not really suitable for our use case here, except of showing you something. And you always have to look also into a more specific, into your use case, into your business case, and have to adapt your models, especially to these business cases. And that also means make them smaller from an architecture-wise. Any more questions?
Okay, if that's not the case, then thanks again. If you're getting questions in the break, just get up to us and let's have a chat or see you around. All right, thanks.
Thanks.